Hi everybody. Today we're going to discuss why spacetime curvature was introduced into general relativity. And the reason I'm making this video is because most of the explanations of spacetime curvature that you will see are wrong based on the development of general relativity and the mathematics. Spacetime curvature in the internet and on YouTube is being used to do a job that it was not meant to do. So, in order to prove my point and not just be a nutter on the internet, just saying stuff, let us go to the equivalence principle, which I think we can all agree with, and I will be checking off these as we go that we all agree that these are true. So, what the equivalence principle is, in a uniform gravitational field, gravity is indistinguishable from being in an accelerated reference frame. I think we can all agree that this is what the equivalence principle is. But mathematically, what does that do? Well, it redefines inertial frames as being in freefall. And this is the mathematical framework that you need to use if you want to do general relativity in a small local uniform field. This is the mathematical framework that differs from Isaac Newton's framework, where the surface of the Earth is inertial and apples are non-inertial. This is not just a cute trick. It is the mathematical language of the equivalence principle. And we're going to go through these arguments step by step. So we can all agree on the equivalence principle. We can also agree that mathematically, in terms of the pure mathematics, this redefines frames as freefall, inertial frames as freefall. By definition, this is what you would get if you took the equivalence principle at face value. So we can agree on all of these premises. Isaac Newton says inertial frames only make sense if they accelerate relative to each other. We will accept this premise, but we're going to put an asterisk next to it. But we would all agree that this is true, that inertial frames a coordinate system that you're using as a standard to measure acceleration only makes sense if it does not accelerate relative to another coordinate system that is inertial, because you're using those coordinate systems to measure acceleration. So if they both accelerate relative to each other, then you cannot, you would lose any sort of sense of measuring accelerated frames versus inertial frames. So Newton says the Earth is inertial and apples are non-inertial, and you need two apples to do this experiment. You cannot use only one. If you see any video using only one apple, or you see an explanation on the internet only using one apple to explain space-time curvature, then it's wrong. And you'll see why we need two apples in a bit, but it has to be two apples. We take two apples and we drop them. The Earth is inertial, the apples are non-inertial. Einstein says, according to your own definition, Newton, you can take the free-falling apples as being inertial, and the surface of the Earth accelerates up to meet the apples. No force is required, only that the surface of the Earth accelerates up to the apple. The apples are consistent with Newton's inertial frames. So, in uniform fields, free fall is an inertial frame, and it's consistent with Newton's definition of inertial frames, and is in fact better because accelerometers agree with Einstein. So, falling is due to an inertial object being in a non-inertial frame. That is true. Mathematically, that is a true statement, even according to Newton. Even Newton has to agree in this scenario. Newton has to agree. But Newton is furious, and he immediately goes to non-uniform fields, because he should say that in non-uniform fields, you can't say that these apples are inertial because they are accelerating relative to each other. So he's and orbits. How can a free-falling apple be inertial whilst a satellite, which is constantly changing direction, and remember, a change in direction is an acceleration. How can an apple and a satellite both be inertial paths when they are accelerating relative to each other? So Newton flips it back to Einstein and says, no, your definition of inertial objects being in free fall is not the same as my definition of inertial frames. So I'm not wrong, you're wrong. The surface of the Earth is not accelerating upwards at 9.8 meters per second squared. That would be ridiculous. It would be stupid. This is just a mathematical trick that you've used in the equivalence principle. It has no further significance. So Newton says in non-uniform fields, free-falling objects accelerate relative to each other. Therefore, Einstein's statement that free fall is inertial is false. So what Einstein does is move the definition of inertial frame to a geodesic on a spacetime manifold, and if geodesics are on curved surfaces, they can accelerate relative to each other. And before Isaac Newton can object to this changing of the goalposts, Einstein says that his new definition of inertial frames will mimic Isaac Newton's definition of inertial frames in flat spacetime. So that Newton's definition of inertial frames is almost true, but it is not completely true. It is an approximation in when spacetime is flat. When spacetime is not flat, Isaac Newton's definition of inertial frames is false. So, but what does this mean for the surface of the Earth? Does this mean that the surface of the Earth is inertial? Well, no. The whole point of the arguments that were made by Einstein were to preserve the fact that the surface of the Earth is still non-inertial and that it is apples and satellites that are inertial. So spacetime curvature is not being used to explain why an apple or a satellite fall to the Earth. Spacetime curvature is the reason why an apple and a satellite can still be inertial paths despite the Earth's surface, to be precise, being non-inertial. So when you see these visualizations, so this is a common visualization where you have the Earth and you have a satellite going around the Earth or an apple falling towards the Earth. What you are seeing is, of course, there is curvature. You are seeing a curved surface, so you will be seeing some curvature here. But what you are actually seeing properly is a mass-induced coordinate transform, and it is a non-inertial coordinate transformation, and a non-uniform, non-inertial coordinate transformation will cause the curvature. And that is the curvature that you're seeing. The curvature that you're seeing is the deviation of these straight lines. So this is a straight line, and this is also straight. And yet they deviate. So this would be tidal forces. The reason why people think that this is a satisfactory visualization of falling inwards due to gravity is that they assume, like Newton, they're siding with Newton, that the surface of Earth is inertial. But this is not good because you cannot be on Newton's team for the definition of inertial reference frames and still accept general relativity. You must either accept that Isaac Newton is correct, that the surface of the Earth is inertial, and that it is the apple that is non-inertial, or you must accept that it is the apple that's inertial and the surface of the Earth is non-inertial. You are not able to hold both of those views. Spacetime curvature will not step in to save the fact that the surface of the Earth is in fact inertial. Spacetime curvature is not doing that job. The job of spacetime curvature is to produce tidal forces which allow geodesics in spacetime to diverge or converge. but the surface of the Earth is not a geodesic. So this is an incorrect statement. We should say that this is non-inertial. And therefore, when people show you this model, they are showing you a mass-induced non-inertial coordinate transform and the non-uniform transform, essentially mimicking a acceleration outwards in all directions, causes the curvature that you see, which will allow satellites and apples to accelerate relative to each other. So general relativity was constructed on the foundation that the surface of the Earth is not inertial. The whole premise of general relativity was to square the fact that on the surface of the Earth, you are not in an inertial frame according to the equivalence principle. And that is why the equivalence principle is true. And this is why you can get space-time curvature emerges as a result of it. It is not, space-time curvature does not cause the equivalence principle. The equivalence principle causes there to be space-time curvature. So T, R, theta, and phi are the coordinates centered at Earth. We have the Schwarzschild metric, and the radius is only defined beyond the Earth's radius. And as we've discussed, this is a non-inertial coordinate system. And if you do the equations of motion on a non-inertial coordinate system, you will get pseudo forces. And that pseudo force that you would get is gravity. So gravity emerges, and we will see this when we're going to crank through. We'll crank through the equations of motion, and what we see is that we have the proper acceleration, we have a Newtonian gravity, we have the time dilation factor, which is essentially one for non-interesting cases like things falling to the Earth. So don't worry about this guy. It's a constant. It's just one in easy cases. And this guy will reduce to Newtonian gravity. And we have an extra term, which is a seemingly repulsive force that is close to the event horizon. But this repulsion is only observed in the coordinate system of the Earth. If you were the person falling into the Earth, if you were the apple, you would not experience any of these forces. You would only experience falling in to, you would be in free fall, you would be in an inertial frame, you would be fine. And if you were rotating around the Earth, we have some centrifugal forces due to rotation. Now, the blue letters are variable for a single object. Remember, I was mentioning you need two objects to see curvature. This is for one geodesic, you will not see any curvature. One geodesic, which is one choice of starting variables. For one geodesic, you will not observe curvature. Curvature is large scale, and you need multiple geodesics. You need multiple infalling objects to see it happening. If you do not have multiple geodesics on your surface that you are watching, you cannot say whether there's curvature or not because you cannot observe what they do with respect to each other. So one choice of starting coordinates. So this would be taking one value of r and one value of theta. If you were to take two choices of starting coordinates, this would be the equivalent of taking two objects and starting them at different positions. then you will get tidal forces. And the size of these tidal forces will be dependent on how large of a region are you looking at. So over small regions, so here is a box with 2 apples falling. There is 0 curvature here. This is too small. It's too small to see. So almost 0. If you take a large region, now your apples will accelerate relative to each other. You will see curvature. And that is what these little blue and red symbols are demonstrating, is that if you change what these numbers are, so these are your numbers that in your coordinate system that you can change. If you change them, your geodesics will be different because of the non-inertial frame. The non-inertial frame will mean that if you change the positions at which you start, you will get curvature as a result, and the curvature will be dependent on how distant your starting coordinates are from each other. So the non-inertial coordinate system of Earth produces the pseudo force of gravity and causes spacetime curvature as a result over large regions, and these are measurable tidal forces. So if you see any videos showing you coordinate transforms like this, where there's one apple, and here's the surface of the Earth moving up, and here's time, like this. This is a coordinate transform into a non-inertial frame. And this is gravity. This is completely valid to be gravity. You're still demonstrating gravity, but this is not spacetime curvature. And this is a massive confusion. I was very confused for about a year, and especially when I was doing my relativity module, where I had to do an exam on this stuff. And you have to use these equations. This is not spacetime curvature, because if I draw another geodesic on this surface, you can see, look, the deviation of these geodesics is essentially 0, because we are modeling a uniform field. And uniform fields are not curved. They don't need to be curved. A uniform field doesn't need to be curved because a uniform field is a non-inertial frame. It is an accelerating frame, accelerating upwards, as it were. It doesn't need to be curved to produce gravity, because the gravity is not coming from the curvature. The curvature is used to make the definition of inertial frames consistent. Sorry, not spacetime curvature. If anyone has any issues with what I've said, or they have any questions, please drop comments, definitely. And yeah, that's it.